Welcome you all to Unit 7. Now today we will continue on our previous video. So today we already discussed numerical differentiation using forward, backward and central difference. Today we discuss high accuracy differentiation formula and Richardson extrapolation. Now just to revise, we have forward difference based on the next point. Similarly, if we want to take the second derivative, we use the same Taylor series and come up with this formula. So for backward, we use the previous point. For first derivative, similarly we can extend it to up to second order based on the points. Just plug the first order differentiation in the Taylor series and you come up with this formula. Central difference, if you remember, we use both forward and difference points to calculate the central formula. So this is the central formula which has much better accuracy as compared to forward and backward. We can use this to extend for the second order differentiation. Now today we will look for high accuracy differentiation formula. Before going to this, from the previous video we understand that if we reduce the value of h, we have much better accuracy. So the next thing we can see from the central difference is that if we use more points, we can have better solution. Now in high accuracy differentiation formula, the idea is to include more points so that we can have better approximation of the differentiation. So in high accuracy difference formula, we use more points to calculate the differentiation. Now high accuracy divided difference formula can be generated by including additional terms from the Taylor series expansion. So if you remember, this was our Taylor series, so we can rearrange it and we have this formulation. Okay, so if we previously we know that this is the second order that we calculated in previous slide. If we use this point in the first one, we come up with this formula. So if you look here now we are using more points. For example, so we have xi, we also have xi plus 1 plus 2. So this means that more points are involved in calculation. So that's why we have error term is in terms of h square. Okay, previously this was in terms of h, now it is improved to h square. And similarly we can rewrite this formula, so we can have this compact formulation, so its accuracy is of h square. Now if we look for the forward first order differentiation, so we use 2 points here, we use 3 points to come up with this solution, and we have better approximation of the first order. Similarly, if we go for the second order, we can extend this up to second order as well. So as we did in the previous slide, that we come up with the second order, so we can extend this. So the idea here is that if you include more points, you have better accuracy. Now we can extend it to third order and also up to fourth order. Now if we move to the backward, we can have the same thing for backward as well. So we are using other points than the forward one, but we can improve this accuracy from h terms to h square. So this means that your error is much less when you are using high accuracy formulas. So it can be written for second order, similarly for third order as well. So the first formula in the third order is without including the more terms, or not the high accuracy, but the second is including more terms with high accuracy formula. Similarly, it can be written for fourth order. Now we can extend this formulation to the central, where we can have better approximation of h square. When we use this, it is further improved to h power 4. So we can have first order, second order, third order and fourth order, as we have in case of forward, backward and backward formulations. Now we see how this high accuracy formula affect on the uh, accuracy of the solution. So let's see. Now what we did here is that we use high accuracy formula, but with h is 0.25, so we reduce the h as well. So let's see how much accuracy we can get from this. So this is the same example as in previous video we use for forward, backward and central difference. So we calculate the true value. After that we just come up with the points, because now we need more points. So the idea is the same, use x value as the base and you use h to calculate all the points. So from there we need the function values, and the next step is very simple. Using these function values, plug in these formulas. So we have forward, backward and central. So when we do that for same point, so look here, for forward our percentage relative error, true relative error is 5.82%. This is much improvement. Similarly for backward is 3.77%. So surprisingly, if you look for the central, it is 0%, is the accurate one. So now question is why it is accurate? Because we still use the approximation. Now here accuracy is based on the number of significant figures. If you look at, we are using only 4 significant figures, so that's why accuracy is based on 4 significant figures. If you use more significant figure, you still have error. The idea here is that the error is much less, that can be neglected in this case. So this is the main idea of high accuracy formulation. Now what we learn from here is that, as expected, the error for the forward backward difference are considerably more accurate from the previous case. However, surprisingly, central difference yields a perfect result, but for these only number of significant figures. Okay, this is because the formula based on Taylor series are equivalent to passing polynomial through the data points. Okay, now this is an example that you can do by yourself. Just do a practice example. So this is the function value, this is x, so you can use x plus hi to come up with the points. Okay, so now from these points you just plug the formula and you can solve it. Now we will move to the next one, which is very important, and the last topic of this numerical differentiation is known as Richardson extrapolation. So in previous high accuracy formula, we improved the accuracy including more points. Now here there's another way that we see previously, that is, if we reduce the value of h, we can have better result. Now here what we are doing here is that we are using interpolating, means that we are using two formulas, but we are using the best formula, not forward not backward. Instead we are using the central formula, and we are using the value with h and h half to come up with the formula. So the idea is that we use the central difference, which is better formula than forward and different, but we are using different step size as a part of formula so that we can have better accuracy. So Richardson's extrapolation is based on that formulation. Now let's see. To this point we have seen there are two ways to improve derivative estimates when employing finite divided difference. One is decrease the step size, other is use higher order formula. Now the third approach, based on Richardson explanation, use two derivative estimates to compute the third one, more accurate approximation. So we are using two. So how we do that? Actually the idea is that this provides the mean to obtain an improved differential estimate difference. D is for difference, okay, using the formula. So what is this difference? This is actually central difference, okay. So D actually represents the central difference formula, okay. Remember that. Now we come up with this formulation. How we come up with this formula is very easy actually. If you calculate the central difference for H and also calculate the central difference for half of h. When you do that for half of h, so what happened is that, because if you remember, we have the higher term based on h square, so when we half it, it is 4 times. So this 4 is coming from there, and then we use we subtract from half difference formula to the original formula. When we do that, we come up with this formulation, and we use this formula to calculate the differentiation. Okay, so this is known as Richard extrapolation formulation. So it gives much better results. Let's see. Now it only applies to central difference. I told you before, D is actually central difference. So H2 means that H is divided by 2. H1 means that H is the original value. Okay, so approximation is of H square. In the center, when we use this formula, approximation goes to H4. So this means that it has much higher accuracy as compared to the center formula. Now let's do an example, same example, but here we are using H.5 and 0.25. So two H is used. So we have same formula, same true value. Now we calculate the D. D is the central difference I told you before. Now just calculate D. D is, this is the formula for central difference with H. Now you put H value 0.5, you come up with minus 1.5, similarly 0.25. Now apply the Richmond formula. So when you apply the Richmond formula, you see that you get the exact value, true value for 4 significant figures. So this means that we get a perfect results. So this means that this Richardson extrapolation method really improve it. Now the idea here in this method is that you can use next differences as well. For example, if you use two difference, one is based on H, other is based on half of H, but you can use other difference as well for this formula, that one is based on half of H, other is based on quarter of H. Similarly, you can improve this further. So from this way we can come up with a table. So look here, this is a table. So it has columns and rows. So if you look at, as we move in the rows, we have higher order power goes up to H4, H6 and so on. So this means that this will, if we move in row forward, we can have much better accuracy. Similarly in column as well, if we move in columns, we are reducing H. So this means that in column and rows we are improving the separate accuracy. But if we are moving in diagonal, we have much better results because we are reducing H and also we are improving the higher order term, that we need more points to include into it. So this means that, so in first column, which is very important, so if you see that is written as D00. What means by D00? This represents the central difference with original H value. Okay. Now if you move to the next value, which is called as D10, it is calculated when you are first time half the H in forward in central difference. Similarly H2, when you 2 times half the central difference H, and similarly quarter and so on. So the idea is that as you move in the column next value, you just have to half the H all the time. So in this way you can fill up this column from basic equation. Now how you fill up the next column, that is D11. You actually use the formula that is given in previous slide, that you have 4 times the half value. So you use 4 times this value. Okay, this is the half value. You use this value 4 times minus this value divided by 3. So you come up with this result. Now how you calculate this one? Same thing. You use 4 times this value minus this value divided by 3. You come up with this. Similarly for this one, 4 times this value minus this value divided by 3. You come up with this. So this is the second column you will easily write using these values from the first column. Similarly, if you want to move to the next column, now here you are using the 4 times. If you are using further, so you have to use the 16. So here if you want to calculate this D22, you have to use these two values. Okay, how you use the similar way as you use the previous, but here you have to multiply by this value with the 16 instead of 4, because you are further, you look here, this is H square, this is H4, so you have to take the square of 4, so it is 16 times this value minus this divided by 15. You come up with this result. Similarly for this one, 16 times D31 minus D21 divided by 15, you come up with this value. When you are moving this, so 16, then you again multiply 4, you have come up to 64. Okay, now here you have to multiply this value with 64 minus this value divided by 63, you come up with it. So this is the way you can come up with this table. Okay, now it's very difficult to remember this, so we come up with a formula to simplify ourselves. Now formula is that, so evaluate to see how this example works. So there's a function and we have a value here, so we will use Richardson and we are asked to calculate 2 2. Now it's not straightforward to calculate 2 2, okay, because if you see previously we are in second column, so we can, how we can calculate this. So we use the simple formula to do it. So we have to calculate the central difference. This is the first step. This is represented actually D00. All right, then we will call it D00. Okay, so this is the formula. Now when we use, instead of h, half of h, we call it D10. So look here, D10 with the half of h is 0.1. Now it is, similarly we calculate 20, so we increase the number here, so we are moving down in the column. Actually these are the rows values of the first column, so we just reduce the h here, so we have this. Now we use these two values to calculate this one. Now how we use that, so instead of remembering the technique, so we come up with a formula, generalized formula. So this is the formula, nm. Okay, so you have to put the value from here n is 2, m is 2, just plug in this value and use these values to calculate it. So it's very easy. So if we have this formula, we can easily calculate the Richardson differentiation. So we just plug 1 1, so we come up with this result. Similarly, if we are interested in 2 2, just plug the value of 2 2 2 1, you can easily calculate this. Similarly, you can calculate 2 2 to do this, because this 2 2 is in third column, so we have to calculate 1 1 and then we can calculate 2 2. So it's better to work with the table, so where you can easily fill the values and you can use this formula to calculate it. Now if we look at the table, so this was the table, so we are interested in this value, so we calculate first this using difference formula, then half this D10, D20, then we use this using these two to calculate this. Similarly for this we use these two, from these two we calculate this. So this means that the last one is much accurate solution we are getting. So we just plug the values here and we come up with this solution. So the best estimate of the derivative of the function. All entries of Richardson tables are estimated of the derivative of the function. So the first column are estimated using central difference formula with different h. So observation is that several formulas are available to determine the first order, second order or higher order derivatives. Richardson extrapolation provides higher accuracy estimate of the first order derivative. So thanks you for listening and watching this video. See you in next video inshallah. Okay, bye.